Hi, I'm Chester Davison.
Hi, I'm Jimmy Jacobs,
Hi, I'm Sterling Pendleton.
and welcome to our process control project. We have a terrarium greenhouse humidity controller here, and this is our apparatus. We have a couple grow lights, we have some plants in there, we have a fan, a pump, and a sensor. I'm going to walk you through each of these pieces of our project here. Right here we have a 12-volt pump that feeds into the system in order to control the humidity levels. Right here we have a temperature and humidity sensor that is hooked up to our Raspberry Pi. Right here we have a little 5-volt Pi fan that is always on throughout this process to regulate temperature and humidity. And right here we have a 12-volt submersible pump that is in a bucket full of water. And right here we have our Raspberry Pi. Now we have a couple relays coming off this system in order to provide power to the different devices, and we have a GPIO input-output board.
The objective is to find good parameters for a PID controller. To do this, we must fit our data to an FOPDT model. So we have our time constant here, we have our gain, and then we have our dead time. Whenever we first gathered our data, we noticed that as soon as we turn on our mister, the humidity actually drops in our greenhouse. And this was causing a lot of problems for us, trying to fit it to an FOPDT model. So what we ended up doing is we ended up truncating our data and only starting after the 18th spot, after it had already gone down here. So you can see here, our data looks a lot better. So then we had to fit this data to our FOPDT model. So we import all of our data here, we set it all up. We have our FOPDT model here. Then we want to model it, and then we have this objective here. So the way this works is we have a solution, and we want to minimize it, setting our objective, and here's our initial inputs for that. So that calls our objective function, and then our model data here, we'll call the sim model, passing it all of our initial guesses here, which then ends up calling our FOPDT model, and it just goes through this for loop calling it for each point, and our FOPDT model is the same as this up here. So this, our objective just takes it, and it takes our Y model minus our Y predicted, takes the difference in between those and squares it and adds it all into this single objective variable and returns that. And our objective is to minimize that. So we want to minimize what this function returns. So Python's going to go ahead and do that for us, and then we're going to get this solution here. And then we're going to just pull everything out of that solution, all the data out of that. We have our KP, our tau p, and our theta p, and then we're going to go ahead and graph that. And you can see here that it graphs pretty nicely. And this is our new KP value, our theta p, and our tau p data here. And then we're going to use these, and we're going to plug those into our PID controller. Now that we have the results from our process model, we want to implement them into a PID controller. We're going to use this equation here to create our PID controller. And so we have our bias here, then we have our P, we have our I, and we have our D. And so we're going to take the results here of our KP, our tau p, and our theta p from our process model, and we're going to convert those into our KC, our tau I, and our tau D. So we're going to create these values here, the KC, the tau I, and the tau D. We're going to use an IMC aggressive approach for these just because it takes so long for our greenhouse to adjust to the sprayer. And then we're going to create our PID function here. And this is just going to follow this equation up here exactly. So we're going to create our P, our I, and our D. And so the output is going to be our bias along with our PID controller. And we're gonna clip our results here. If it's anything greater than 0, we're gonna call that a 1. And if it's anything less than 0, we're gonna call that a 0. The reason for this is because our pump can only turn on and off. We can't have our pump 20% on or 50% on. And so this will allow us to either turn it on or off. But we can adjust these to say only turn it on if it's 0.2 or 0.3. We can adjust that in the future if we'd like. Once we have our PID controller set up, we want to create um, uh, a loop here. And so we're going to set a time points equal to 6,000, which is about 100 minutes. And then we're going to create these buckets here to store our values in, so that way we can see a graph at the end. And so we have our H1, our Q1, and then our set point. And then we're going to just set all of the values on our set point equal to 90 here, but you could change that to anything you like. And then for I in range in, for I in our range 6,000, we're just going to set our H1 at I equal to the humidity, and then we're going to call our PID controller passing it all the values. And then we're going to just print out our Q1 to see what that is for debugging. And if it's equal to 1, we're going to turn the pump on. If it's equal to 0, we're going to turn the pump off. So this actually worked out really good for us. We're able to make everything work, and we were able to get a really good PID controller, and it went really fast for us. The humidity adjusted really quickly in the greenhouse, which made our data look really good.
Now moving into our results section here, we have a graph of a successful trial run of this controller. The set point was 80% humidity. When we started this trial, the humidity in the greenhouse was just above 90%, and so the controller responded well, allowing it to drop until the humidity level dropped below 80%, and then kicked on the pump for a longer period of time in order to get the humidity level back up, and then it did very well at maintaining the just above the set point here for the duration of this trial. And all in all, we're very impressed and happy with the results of this greenhouse humidity controller.